So our next talk this morning is going to be by Chenoa Tremblay. He's going to talk about the chemical cause of the Galactic wild. Special line.
AKA. So as Tessa mentioned yesterday, I'm the lead of the Galactic and Extragalactic Spectroscopy group for the MWA. And there's been a lot of exciting new projects. It's not just me anymore. So I wanted to give a separate update on what this group is doing in particular. So there's a number of projects that we're doing with the MWA that are currently active. Our newest one is an Axion dark matter search, which is a multi-frequency, multi-instrument campaign to try to detect dark matter through interactions in something that should look like a spectral line. So this is a group made up of theorists, spectroscopists, and other levels of physics put together, and I'm helping with the MWA data reduction with that. And they're working on taking some of the cubes that I had made as part of my PhD thesis and starting to figuring out how they can use this data to look for these dark matter particles. Otherwise, we've got some other projects, recombination lines, high redshift H1, and various other things that I'll talk about. So carbon recombination lines at the moment is being led by Slava Kitov, and this is a project that had started with a master's student at University of Western Australia a few years ago. There was a lot of data taken in 2013, 2014. Unfortunately, a lot of that data was the observations were set up incorrectly, the tiles were saturated, none of the data was useful, so we were able to get new observations that were taken in April 2019. And part of the idea of this experiment is not just the recombination lines, but it's also use spectral lines to test new supercomputing possibilities for regional centers for the SK load. So that is work that Slava's leading at the moment. There's two high redshift H1 searches, one that's led by Rick Seymour that is more doing follow-up with ALMA, and then one that's doing a blind search with James Allison. At the moment, James and I have spent the last 6 months developing a pipeline for this work and getting it working on Magnus at the Pasi Supercomputing Center. And as a test case, we've got record time to look at this source PSOJ352, and it's a known redshift quasar at 5.1, and I've started downloading data and working on the processing of that at the moment. My postdoc at the moment at CSIRO is looking at dark magnetism, which is the magnetic fields in dark molecular clouds where there's active star formations, using the molecule CH, which is a good tracer of H2 molecular gas in both diffuse and dense gas environments. And with the MWA, I'm combining this search with carbon recombination lines in a molecular cloud W51. And the idea is that both the carbon recombination lines and the CH both require ionized carbon, but the recombination line should only be seen in the diffuse gas, and the CH can be found in diffuse and dense, so it adds better constraints as to what features are coming from where in the cloud system. We're redoing or extending out the galactic plane search for the molecular lines that we had done before. In using the long baselines, we have a much better resolution of the sources, and we're increasing the amount of time, and all of this is done as a co-observation with the Axion project, carbon recombination lines, and we can use it for other science as well. Most of the time I'm going to be talking about these other two surveys. So Orion is an extended survey I had done extension on survey I had done previously, where we had found a bunch of signals within the molecular cloud systems. And we're doing this with the long baseline, getting some greater frequency coverage and longer integration. A lot of this is being used as a data set to train some people at SHAO, the Shanghai Radio Observatory. And they wanted to learn how to process some of these data so that they could also look at extending supercomputing facilities as well. The main project that I've been working on at the moment is doing a deep survey with the long baseline with 30 hours of data on the Vela molecular cloud, or the Vela supernova remnant. This is a particular interest just because there's so many known molecular environments that have been studied over time, but there's not a lot that has been able to link those up and see if there's other interesting aspects of the supernova remnant itself. So this is the supernova remnant, the Vela molecular ridge, which is really well studied, RCW38, which is a star-forming region that's almost as dense as Orion, and then the Gov Nebula, which has a bunch of H2 regions. So far I've processed 15 hours of the long baseline data to stack, and this is over 5 nights. So each night what we're finding is that it's got completely different sensitivities and some other dramas. So each night hasn't been able to be reproduced. Each night has about 30 hours of data, about 36 observations. We have 91 tiles that were active, and these were done in 2018. 2 nights in particular that I wanted to point out were this one and this one. So the bottom one, you can see the really big negative wells. This is some severe RFI that we didn't find until you look at the dirty images of the fine channels, and it can make the deconvolution a lot trickier, and so it's trying to throw that night out. But the one at the top, I can't see it, but if I zoom in, you can see that there's some major structure in the sources that shouldn't be there. At first I was thinking they kind of looked like that. Now we realize they all look like ducks. So we're calling this the Night of the Living Ducks. So we've looked at this in a number of different ways. So this is an every 5-minute snapshot for all 36 observations for the whole night. So I took one of the snapshots and broke it up into 30-second intervals to see if the sources were really changing over time, and there isn't a dramatic change over time. The PSF looks fine, and the dirty images show the same structure as well. I have still no idea. Talked to the operations team, and they said all the calibrators for the night look fine, all the ingest looks fine. They don't see where any of this is coming from. So if anybody wants to help me explore where ducks in space came from, I'm happy to listen to your ideas.
I've got no idea where it is, but I've seen it in an email, so
Okay.
obviously a duck. Not always like a duck. Sometimes it's a long duck.
Some of them have nice little ripples around them, so that, you know, they enjoy the info, but... So for those of you that don't know haven't seen my talks before and haven't seen how my pipeline works, the idea is that I take about 2 to 5 minute calibrated snapshots, peel any bright sources, and then image every single coarse channel and every single fine channel from the MWA. I'm taking the coarse channel information, comparing the continuum sources to various catalogs, doing positional flux and primary beam correction, and applying those corrections to the individual fine channels. Stack all of the observations up, very carefully regridded, so that they all have the same WCS coordinates and we don't smear out the sources. And then subtract the continuum and have a continuum subtracted cube that I'm looking for. So out of the 15 hours of data that we have reduced so far, there's about 7.5 of actual usable data. So I've been looking at the noise properties of these. So 104 observations from the 3 nights. I took one coarse channel and looked at what the noise looked like across all 104 observations. They're pretty stable across these nights. And then there's a couple of them that we've thrown out just because of really poor noise. As you're stacking them, you should expect that the sensitivity goes down as prior to time. And we are roughly seeing that, and there's some wobbles in this information, and then I'll explain that in a couple minutes. If I take a single cube and look at how each of the fine channel noise looks, it looks pretty good. The central one's always zeroed and flagged, and I wasn't sure if people knew that. And if I look at the noise through a histogram of pixel information and take a log of that, you can see that the noise itself is not Gaussian. And that's because when you stack all of this, you get an RMS plot that looks like this. And it's easier to see over here where it looks like a series of stacked sheets that are all kind of off from each other. And that had to do with the way that we ended up having to do the imaging. So for these, normally, the sources were quite close to the horizon. And when you do that, you end up with a large number of W terms. So I used this piece of code written by Andre Offringer that allows you to change the phase center something closer to the to zenith, so that you reduce your number of W terms so that your imaging is complete within the wall time of the supercomputer. When you do that, though, it changes the coordinate system a little bit. And so when you regrid everything, your observations start now have actually been imaged slightly different parts of the sky. And this isn't a problem when you have something like Gleam where you have drift bands, but in order to image all of the fine channels within a particular coarse channel, within the memory resource of the supercomputer, you can only image a small piece of the sky that's available to us. So those aspects convolve onto each other has created this strange pattern when we stack the images. So that's why the noise itself is not Gaussian unless you look at a very specific sensor where most of this data actually overlaps. So in order to do this, what I've done is taken that noise map and divided it by each of my channels, sky images, and then you can actually get fairly Gaussian noise if you're looking in a signal-to-noise tube itself. So there's a number of data processing challenges. So for every single night, I create 87,264 final images, and it's the 24 3-gigabyte data final continuum cube. It takes about 25 terabytes of disk space for the images and about 50 terabytes of intermediary product space. So for 15 hours processed so far, I've used 260,000 CPU hours. So this is not an easy project. So what we've done is I've gone to POSI and I've gotten approved. We've got 1.5 million CPU hours on Magnus, which is split into quarters. And the spectroscopy group now has their own space on group because I was using all of the space that was allocated to MWA Psi, which was not fair. And going forward, we'll be using this for all of the spectral line projects that are coming up. So all of this is not grim. There's still some interesting stuff we're finding in the data. So just on Friday, I started looking through things and have found a couple of potentials which we're looking into, and a few more which is persistent. There's a number of stars throughout the field that look like this that both have these signals even though they're relatively weak, still may be particularly significant, so we're looking into that as well. Thank you. Alright, thanks very much. Does anyone have any questions?
No? Yeah, I guess I'm just curious what the significance of the lines that you showed at the end there. Are those lines that have been seen before, or are those new?
Everything at these frequencies is new. No one's ever looked below 700 megahertz before I started this work. So they have been detected at higher frequencies, so it's not inconceivable, but it will be interesting to look into this a little bit more to see if at these locations can we see other transitions of, well, we only, this one is, this molecule, this is the only transition in the entire frequency range, 6 million, but this one has a couple others, so it might be interesting to see if we see some of the other ones. NO is showing in the same kind of regime around stars as OH does. The other one is unknown. The chemistry is a little bit rare, especially since it's deuterated. So that means that it's like a heavy hydrogen, and those tend to trace more new star formations than tend to be the actual stars.
So obviously with this stuff you have a problem with frequency resolution.
Yeah.
I think they're something like 30 kilometers per second channels, aren't they?
No, these are, at these frequencies, these are about 20.
I was just wondering what your what your plans will be when you can have more frequency
Absolutely.
resolution.
It would be going back and finding the most interesting stuff and trying to go back and reobserve it. Or, yeah, I mean, learning a lot from doing these longer integrations as it is. And so hopefully taking that learning in combination with being super better frequency resolution to see if we can actually start looking at the kinematics of this and not just the system.
Well, and also have really
good confirmation.
Yeah, exactly. Anyone else have any questions?